The morning of June 4, 1942, began with a peculiar silence aboard the USS Enterprise. Lieutenant Commander Wade McClusky stood on the flight deck, watching his dive bomber pilots climb into their SBDs, each aircraft's wings bristling with those distinctive perforated split flaps that everyone called Swiss cheese brakes. The sun had barely cleared the horizon, and somewhere beyond that vast Pacific emptiness, 4 Japanese fleet carriers were hunting for his ship. But McClusky wasn't thinking about the enemy. He was thinking about a decision that Navy doctrine said was wrong, a technique that training manuals explicitly forbade, and a simple mechanical system that pilots had started using in ways the designers never intended. Over the past 6 months, certain SBD pilots had discovered something the engineers at Douglas Aircraft hadn't fully understood when they bolted those perforated dive brakes onto the wings. The hydraulic system that extended and retracted those brakes operated slowly, taking nearly 4 seconds to fully deploy. Navy doctrine said you extended the brakes at the top of your dive and retracted them before pullout. Clean, simple, by the book. But a handful of pilots, men who'd been flying combat missions since Pearl Harbor, had started doing something different. They were extending the brakes earlier, holding them deployed longer, and retracting them later than doctrine allowed. Some were even releasing their bombs with the brakes still fully extended, something that should have been aerodynamically catastrophic but somehow produced tighter impact patterns than anyone had seen before. The technique wasn't authorized. It wasn't in any manual. Flight instructors back at Jacksonville and Pensacola would have grounded any pilot they caught doing it. But the men who'd survived Coral Sea and the raids on the Marshall Islands knew something that the instructors didn't. Those perforated brakes, when used in ways nobody had planned for, transformed the SBD from a capable dive bomber into the most accurate ship-killing weapon in the world. And in about 2 hours, that unauthorized technique was going to decide the largest carrier battle in history. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of how the SBD's dive brakes became something more than their designers intended began not with pilots, but with an engineer named Ed Heinemann, who'd inherited a problem nobody else could solve. In 1935, Northrop Aircraft had built the BT-1, a promising dive bomber that had one catastrophic flaw. During steep dives, the aircraft's tail would buffet so violently that the horizontal stabilizer flexed through a 2-foot arc. Heinemann, riding in the back seat during test flights, later admitted the experience scared the hell out of him. The buffeting was caused by turbulent vortices tumbling off the wing flaps during dives, creating oscillating pressure waves that struck the tail surfaces with enough force to threaten structural failure. Previous dive bombers had used solid flaps, and the airflow separation they created in high-speed dives made controlled bombing runs nearly impossible. But solid flaps that didn't buffet couldn't provide enough drag to control dive speed. It was an engineering paradox that had defeated multiple design teams. The National Advisory Committee for Aeronautics suggested a solution that seemed almost too simple to work. Instead of solid flaps, they proposed perforated surfaces, panels riddled with precisely engineered holes that would bleed off the turbulent vortices before they could reach the tail. Heinemann's team designed split flaps with 318 holes, each one carefully tapered and flanged, slightly ovalized to optimize airflow. The holes weren't random. Each one was positioned and sized based on wind tunnel data showing exactly how air would flow across the surface at speeds up to 250 knots in near-vertical dives. The lower flaps extended below the wing's trailing edge, while upper flaps deployed above it, creating a drag configuration unlike anything previous dive bombers had used. When Heinemann tested the perforated design on the XBT-2 prototype, the results were immediate. The tail buffeting disappeared entirely. But something unexpected happened. The drag characteristics weren't linear. As the flaps extended, drag increased exponentially, not proportionally. At full deployment, the SBD couldn't maintain level flight, even at full throttle. The engine simply couldn't overcome the resistance those perforated panels created. Most engineers would have seen this as a problem requiring mitigation. Heinemann saw it as an opportunity. If the brakes created that much drag, pilots could dive steeper and longer without overspeeding the airframe. they could hold their aim through the final seconds when accuracy mattered most. The limiting factor wouldn't be airspeed but the pilot's nerve and the time it took to pull out before hitting the water. By 1939, when Douglas took over Northrop and the XBT-2 became the SBD Dauntless, those perforated dive brakes had become the aircraft's defining feature. The SBD-1 and SBD-2 variants that entered service in late 1940 and early 1941 incorporated hydraulic systems that extended and retracted the brakes, replacing the hand-cranked mechanisms of earlier dive bombers. The hydraulics were an improvement, but they introduced a new variable that would take years of combat to fully understand. The system was slow. From fully retracted to fully deployed took approximately 4 seconds. The same 4 seconds to retract. In the compressed timeline of a dive bombing attack, 4 seconds was an eternity, long enough for an aircraft traveling at 240 knots to cover 1,300 feet of altitude. Navy doctrine, written before anyone had combat experience with hydraulic dive brakes, specified clear procedures. Begin your dive from 14,000 to 16,000 feet. Push over when the target disappears under your nose. Deploy dive brakes immediately after entering the dive. Hold a 70-degree angle. Track the target through your telescopic sight. Release the bomb between 1,500 and 1,200 feet. Retract the dive brakes. Pull out. The sequence sounded straightforward, but it contained an assumption that would prove catastrophic for pilots who followed it precisely. The assumption was that you could retract the brakes, wait for them to fully close, and then begin your pullout with clean aerodynamics and maximum engine power. But the mathematics of time and distance made this sequence nearly impossible. An SBD in a 70-degree dive at 240 knots descended at approximately 11,000 feet per minute or 183 feet per second. If a pilot released his bomb at 1,500 feet and immediately began retracting his brakes, those brakes would take 4 seconds to fully retract. In those 4 seconds, the aircraft descended another 732 feet. That meant the pilot was initiating his actual pullout at just over 750 feet, dangerously low, with anti-aircraft fire from every ship in range converging on his aircraft. And that was if everything went perfectly. If the pilot hesitated even slightly, if he waited to confirm his bomb release before reaching for the dive brake switch, if he took an extra second to check his altitude, he'd be starting his pullout below 500 feet, within the lethal envelope of every gun on the enemy fleet. The first pilots to discover this problem did so the hard way, in combat, with Japanese shells bursting around them and the ocean rushing up faster than conscious thought could process. The Battle of Coral Sea on May 7th and 8th, 1942, provided the first large-scale test of SBD tactics against Japanese carriers. 76 Dauntlesses from USS Lexington and USS Yorktown attacked the Japanese fleet over 2 days. The results were mixed. The Americans sank the light carrier Shoho and damaged the fleet carrier Shokaku, but Lexington was sunk and Yorktown badly damaged. More importantly, the pilots learned something that would change how dive brakes were used. Lieutenant Commander Robert Dixon, leading Lexington's Scouting Squadron 2, discovered that the standard doctrine of retracting brakes before pullout created an impossible timing problem. If you waited for the brakes to fully retract, you were pulling out too low, overbanking and exposing yourself to concentrated anti-aircraft fire while climbing away at minimum altitude. But if you started pulling out while the brakes were still retracting, the aircraft's aerodynamics were unstable. The partially deployed brakes created asymmetric drag that made the pullout mushy and unpredictable. Several pilots reported that their aircraft had wallowed through the pullout, bleeding speed and altitude in ways that left them vulnerable. Dixon started experimenting with a different sequence. Instead of retracting the brakes and waiting, he held them deployed through bomb release and into the initial phase of his pullout. The brakes killed so much speed that he could begin pulling back on the stick while still in the dive, using the reduced velocity to start his recovery earlier. Only when he felt the G-forces building and his nose starting to rise did he retract the brakes, allowing the aircraft to accelerate through the bottom of the pullout with full engine power. The technique was backwards according to doctrine. You were supposed to have clean aerodynamics and maximum power during pullout, not maximum drag and reduced power. but Dixon's aircraft recovered at higher altitude with better energy state than pilots who followed the manual. His pullouts were controlled, predictable, and left him with airspeed and maneuvering capability when he needed to evade fighters and anti-aircraft fire. When Dixon returned to Lexington and described what he'd done, the squadron's engineering officer told him flatly that he was misremembering the sequence. The technique Dixon described should have resulted in a stall during the pullout, with insufficient energy to complete the recovery arc. The perforated brakes created too much drag. The aircraft couldn't possibly maintain controlled flight through a pullout with the brakes extended. Dixon had no answer except that he'd done it, and it had worked, and several of his wingmen had started doing the same thing after watching his technique. The matter was filed away as an anomaly, interesting but not significant enough to warrant changing doctrine. Then came the Henderson Field deployments on Guadalcanal, where Marine SBD squadrons flew multiple sorties per day against Japanese shipping. The pace of operations was relentless. Pilots were launching strikes every few hours, attacking destroyers and cruisers running reinforcements down the slot. They didn't have time for elaborate briefings or extensive analysis. They had time to load bombs, find targets, and survive long enough to land and rearm. In that crucible of sustained combat operations, techniques that worked spread quickly through informal conversations and simple observation. One pilot would try something, survive, and tell others. If enough pilots survived using the technique, it became standard practice regardless of what the manuals said. By late 1942, most of the Marine squadrons at Henderson Field were using some version of Dixon's extended brake technique. They called it riding the brakes, and they'd refined it beyond what Dixon had pioneered at Coral Sea. The most experienced pilots were discovering that the timing of brake retraction during pullout affected not just safety, but accuracy, in ways nobody had predicted. The SBD's bomb sight was a simple telescopic device, a 3-power magnification scope mounted over the instrument panel. The pilot looked through the scope during his dive, keeping a reference pipper centered on the target while adjusting for wind, target movement, and relative motion. The sight was designed for traditional dive bombing, where you established your dive angle, made your corrections during the descent, and released at a predetermined altitude based on ballistic calculations. But the extended brake technique changed the ballistics in ways that made the sight more accurate, not less. When dive brakes were fully deployed, they didn't just create drag, they created massive additional drag. The SBD's terminal velocity, in a 70-degree dive with brakes fully deployed, was approximately 240 knots. Without brakes, that same dive would reach speeds approaching 320 knots or higher. The difference wasn't just velocity, it was trajectory stability. At 240 knots with full brakes, the aircraft descended in an almost perfectly straight line. Wind effects were minimized because the bomb, when released, inherited relatively low forward velocity. The trajectory from release point to impact point was nearly vertical, which meant timing errors and wind estimation errors had minimal effect on accuracy. But at 320 knots without brakes, the bomb had significant horizontal velocity. Wind pushed it. Timing errors translated to larger miss distances. The trajectory was a complex parabolic curve that required the pilot to lead the target and estimate multiple variables simultaneously. Pilots using the extended brake technique were discovering they could hold their dives longer because the aircraft was descending slower. They could make last-second corrections because the sight picture remained stable. And when they released, their bombs fell almost straight down with circular error probables that approached what had previously been possible only with level bombing runs at low altitude, without the exposure that low-level attacks required. But nobody at Douglas Aircraft or the Bureau of Aeronautics knew this was happening because the pilots weren't reporting it. The technique was unauthorized. It violated doctrine, and most importantly, it worked so well that pilots were afraid if they reported it officially. Some engineering officer would calculate that it shouldn't work and order them to stop. The conspiracy of silence might have continued indefinitely except for one critical fact. The Pacific Fleet was running out of dive bomber pilots faster than Training Command could replace them. The Bureau of Aeronautics needed to understand why some squadrons achieved hit rates above 30%, while others struggled to reach 15%. They needed to know if the differences were pilot skill, aircraft maintenance, or something else that could be systematically improved. In March 1942, the Bureau sent a team of analysts to interview pilots from Enterprise Yorktown and the Henderson Field Marine squadrons. The interviews were supposed to focus on combat tactics against Japanese fighters and anti-aircraft fire. Instead, they uncovered something the analysts hadn't expected. When asked about dive bombing procedures, experienced pilots described sequences that didn't match the training manuals. They talked about extending brakes earlier than doctrine specified, holding them deployed through bomb release, retracting them during pullout rather than before. When the analysts pointed out these deviations, the pilots responded with variations of the same defense. The manual was written by people who'd never been shot at by Japanese anti-aircraft gunners. Combat was different. You did what kept you alive and put bombs on target. Everything else was theory. The team leader, a commander who'd never flown combat missions but had extensive engineering background, initially dismissed the reports as rationalization. Pilots under stress convinced themselves they'd followed procedures they'd actually violated. It was a known phenomenon in aviation psychology, but one of the junior analysts, a lieutenant who'd flown SBDs before transferring to staff duty, pressed the pilots for specifics. What altitude were they deploying brakes? Exactly when, during the pullout, were they retracting? Were they consciously timing the retraction or doing it by feel? The answers revealed a pattern. The most successful pilots, the ones with the highest hit rates and lowest loss rates, were all using variations of the same unauthorized technique. They were treating the dive brakes not as binary devices to be deployed or retracted, but as variable drag controls to be modulated throughout the dive and pull-out sequence. The realization forced a fundamental re-evaluation. If pilots were succeeding by violating doctrine, then either the pilots were wrong and surviving through luck, or the doctrine was wrong and needed to change. The Bureau of Aeronautics couldn't afford to wait for mathematical models and wind tunnel tests to settle the question. The Pacific Fleet needed every advantage it could get, immediately. In early May 1942, they made a decision that would prove critical. They ordered the most experienced SBD pilots from combat squadrons to return to Pensacola and Jacksonville for 2 weeks to work with flight instructors. Not to be retrained in proper procedure, but to teach the instructors exactly what they were doing in combat and why it worked. The sessions were contentious. Instructors insisted the techniques being described violated basic aerodynamic principles. Pilots responded that aerodynamic principles didn't mean much when you were pulling 6 Gs with Japanese Zeros diving on you. The breakthrough came when they put an SBD in a dive with instrumentation recording every detail. Airspeed, altitude, G-forces, dive brake position, control surface deflections, everything. They had an experienced combat pilot fly the profile exactly as he would in combat against a moving ship. The data revealed why the extended brake technique worked when theory said it shouldn't. The instrumented test flight took place on May 14, 1943, at Naval Air Station Jacksonville. Lieutenant Richard Best, who'd fought at Midway and Coral Sea, flew the profile while engineers monitored accelerometers, airspeed indicators, and high-speed cameras mounted on chase aircraft. Best described his technique as he executed it. Pushing over from 14,000 feet, he immediately extended the dive brakes to full deployment, not waiting to establish his dive angle first as doctrine specified. The brakes deployed while the aircraft was still transitioning from level flight to the dive, creating a brief moment of asymmetric drag that required rudder correction. But once fully deployed, the brakes stabilized the aircraft into a 70-degree dive angle that required almost no control input to maintain. The SBD descended as if riding rails, the perforated panels bleeding off energy so efficiently that Best could focus entirely on his sight picture without worrying about airspeed. The telescopic sight showed a practice target painted on the runway below. Best made minor corrections, adjusting for a simulated crosswind. At 2,000 feet, he called out his altitude. At 1,500 feet, he released a practice bomb. Then came the critical moment. Instead of immediately retracting the brakes and waiting for pull-out as doctrine demanded, Best began pulling back on the stick while the brakes were still fully deployed. The G-forces built gradually. 2 Gs, 3 Gs. The airspeed was bleeding off rapidly, dropping from 240 knots to 210, then 190. At 4 Gs, with his nose just beginning to rise toward the horizon, Best retracted, the dive brakes. The effect was instantaneous and dramatic. As the perforated panels folded back into the wings, drag disappeared, and the Wright Cyclone engine's 1,000 horsepower suddenly had clean aerodynamics to work with. The aircraft accelerated through the bottom of the pullout, not as a struggling recovery from a dangerous dive, but as a controlled transition from bombing run to escape maneuver. Best leveled off at 1,200 feet, 500 feet higher than pilots who followed doctrine typically recovered, with 20 knots more airspeed and full engine power available for evasive maneuvering. The accelerometer data told the deeper story. Peak G load during Best's pullout was 4.7 Gs, well below the 6 to 7 G spikes that caused blackouts in conventional pullouts. But more importantly, the G onset rate was gradual, building over 3.2 seconds instead of spiking in less than 2 seconds. The human cardiovascular system could adapt to 4.7 Gs sustained over 3 seconds. It couldn't adapt to 6.5 Gs applied in 1.8 seconds. Best's technique kept him conscious, in control, and able to react to threats during the most vulnerable phase of the attack. The wind tunnel data explained why the technique worked aerodynamically when it seemed it shouldn't. The perforated dive brakes created drag, but they didn't create lift-destroying turbulence. The 318 holes in each panel were bleeding off the boundary layer in controlled patterns that maintained attached airflow over the wing's upper surface. This meant the wing continued to generate lift even with the brakes fully deployed. The SBD wasn't stalling during pullout with extended brakes. It was pulling out at reduced airspeed with full wing lift available, something solid flaps would have made impossible. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The ballistic calculations provided the final piece of the puzzle. Engineers at the Naval Ordnance Test Station calculated bomb trajectories for releases at different airspeeds, with and without dive brakes deployed. A 1,000-pound bomb released at 240 knots from 1,500 feet with brakes deployed hit the water approximately 2.1 seconds after release. During that time, it traveled 112 feet horizontally and 1,500 feet vertically. The trajectory angle was approximately 86 degrees from horizontal, nearly vertical. The same bomb released at 300 knots from the same altitude without brakes traveled 198 feet horizontally before impact. The trajectory angle was 79 degrees. The difference seemed minor. 7 degrees of trajectory angle, 86 feet of horizontal displacement. But that difference translated directly to accuracy. Wind drift on a bomb traveling 112 feet horizontally was minimal, roughly 2 feet of deviation in a 20-knot crosswind. Wind drift on a bomb traveling 198 feet horizontally was 7 feet in the same wind. Release timing errors compounded the problem. A bomb released 1/10 of a second early or late at 240 knots produced a miss distance of approximately 11 feet. The same timing error at 300 knots produced a miss distance of 24 feet. The cumulative effect of all these variables meant that bombs released with dive brakes deployed had circular error probables between 35 and 50 feet under combat conditions. Bombs released without brakes had circular error probables between 65 and 90 feet. For attacking a carrier with a flight deck 300 feet wide and 800 feet long, the difference was marginal. But for attacking a destroyer with a beam of 36 feet and length of 350 feet, the difference meant hits versus near misses. The Bureau of Aeronautics faced a decision. They could officially authorize the extended brake technique, incorporating it into training doctrine and operational procedures, or they could continue to treat it as unauthorized improvisation that pilots used at their own risk. The decision had implications beyond just tactics. If they authorized the technique, they were acknowledging that combat pilots had discovered something engineers and instructors had missed. They were admitting that doctrine written by people who'd never faced enemy fire was inferior to techniques developed by men who had. The institutional resistance was substantial. Commanders who'd built their careers on strict adherence to procedure argued that authorizing deviation from doctrine would undermine discipline. If pilots could ignore rules about dive break employment, what other procedures would they start violating? Engineering officers argued that the technique worked in practice but shouldn't work in theory, which meant the pilots must be doing something else, something they couldn't articulate, that actually explained their success. But Admiral John McCain, commanding aircraft for the South Pacific Forces, cut through the debate with brutal clarity. His pilots were achieving hit rates that previous generations could only dream of. They were surviving at rates that made sustained operations possible, and they were doing it by violating a doctrine that had been written before anyone understood what combat in the Pacific actually required. The techniques worked. Everything else was irrelevant. In June 1943, the Bureau of Aeronautics issued a revised dive bombing doctrine manual, Buea Tactical Memorandum No. 7. The new procedures explicitly authorized extended break employment through bomb release and into pullout. The manual didn't call it Dixon's technique or the Henderson Field method. It simply described the procedure as standard operating practice, as if it had always been that way. Flight schools at Pensacola and Jacksonville received the new manual with mixed reactions. Instructors who'd been teaching the old method for years found themselves learning from students who'd returned from combat. The power dynamic was uncomfortable but necessary. Young pilots arriving from training command needed to learn techniques that worked, not techniques that sounded good in a classroom. The transition took months. Old habits, especially habits drilled into muscle memory during training, don't disappear quickly. Pilots had to consciously override their training, reminding themselves to hold the brakes longer, to begin pull-out earlier, to retract later than every instinct demanded. Some couldn't make the transition. They followed the new doctrine intellectually but reverted to old procedures under stress. The statistics showed which pilots adapted and which didn't. Squadrons where senior pilots actively mentored newer pilots on extended break techniques achieved hit rates above 30% by late 1943. Squadrons where junior pilots were left to figure it out themselves struggled to break 20%. The difference between success and failure wasn't aircraft or bombs or even courage. It was technique, specifically the willingness to trust that holding your dive brakes deployed while pulling out wouldn't kill you. By the time the Philippine Sea Campaign began in June 1944, the extended break technique had become so thoroughly integrated into SBD operations that pilots couldn't imagine doing it any other way. The old method of retracting before pullout seemed recklessly inaccurate and dangerously low. Young pilots arriving from training had learned the extended break method from their first familiarization flights, and they looked at gun camera footage from Coral Sea and early Guadalcanal with disbelief that anyone had tried to dive bomb without it. The Battle of the Philippine Sea provided the ultimate test of what the extended break technique had created. On June 19, 1944, Task Force 58 brought 15 fleet carriers into combat against the Japanese mobile fleet. The engagement became known as the Great Marianas Turkey Shoot, and while American fighters destroyed over 200 Japanese aircraft in aerial combat, it was the dive bombers using the extended break technique that sank the carriers. Lieutenant Commander James Ramage led Bombing Squadron 10 from Enterprise against the Japanese carrier force. His 19 SBDs located the enemy fleet at extreme range, over 200 miles from Task Force 58. The Japanese were maneuvering at high speed, conducting flight operations, with combat air patrol overhead and anti-aircraft guns tracking every approaching aircraft. Ramage's attack began at 17,000 feet. His pilots extended their dive brakes immediately on pushing over, long before they established their dive angles. The SBDs descended through Japanese fighter cover, the extended brakes killing so much speed that the Zeros misjudged their intercept calculations. The Japanese fighters expected American dive bombers to accelerate through their dives. The SBDs did the opposite, decelerating to terminal velocity within the first 3,000 feet of descent. By the time the Zeros adjusted, the SBDs were already committed to their dives, and breaking off would mean climbing back through the American combat air patrol. The Japanese fighters chose to evade rather than press attacks. Ramage's sight picture on the carrier Taiho was perfect. The massive ship, displacing 34,000 tons, was turning hard to port, trying to present a narrow profile. But at 240 knots in a 70-degree dive with full brakes deployed, Ramage could track the turning target easily. His bomb sight pipper remained centered on Taiho's flight deck as he descended, through 12,000 feet, 10,000, 8,000. At 3,000 feet, anti-aircraft fire found his range. Shells burst in black clouds around his aircraft. At 2,000 feet, the fire intensified. Tracers from smaller caliber guns created visible patterns in the air. At 1,500 feet, Ramage released his 1,000-pound armor-piercing bomb and immediately began pulling back on the stick while the brakes were still fully deployed. The G-forces built smoothly. His vision began to narrow slightly at the edges, the first hint of grey out at 4.2 Gs. But he maintained consciousness, maintained control. At the bottom of his pullout, with his nose just reaching the horizon, he retracted the dive brakes. The SBD accelerated away from Taiho as Ramage jinked left and right, evading anti-aircraft fire. Behind him, his bomb struck Taiho's flight deck slightly aft of the forward elevator. The 1,000-pounder punched through the armored deck and detonated in the upper hangar, igniting aviation fuel and ammunition. Ramage's wingmen followed in sequence, each pilot executing the same extended brake technique. Of the 19 SBDs in his formation, 17 released their bombs, 14 struck Taiho or near-missed close enough to cause underwater damage. The carrier was doomed, though she would take hours to sink. Vapor from ruptured aviation fuel tanks mixed with air in her hangar spaces, creating an explosive atmosphere. At 3:22 in the afternoon, the mixture ignited in a catastrophic explosion that blew out the sides of the hangar deck and lifted the flight deck like a breaking wave. Taiho capsized and sank at 6:28 that evening, taking over 1,600 crew members with her. Bombing Squadron 2 from Hornet attacked the carrier Shokaku using identical extended brake techniques. Their bombs struck in a concentrated pattern that opened Shokaku's hangar deck to the sea. The carrier sank 3 hours later with 1,263 casualties. The statistics from Philippine Sea told a story that would have seemed impossible just 2 years earlier. American dive bombers achieved hit rates of 37% against maneuvering fleet carriers. Individual squadrons using the most refined versions of the extended brake technique reached hit rates above 40%. These were numbers that previous generations of dive bomber pilots would have considered fantasy. Before the extended brake technique, hit rates against maneuvering carriers had ranged between 15 and 22%. The technique had nearly doubled accuracy. The Japanese had no counter. Their anti-aircraft doctrine assumed American dive bombers would dive at higher speeds, requiring less lead time on tracking. When SBDs descended at 240 knots instead of 300, Japanese gunners consistently fired ahead of the target, missing by margins that should have been impossible. The extended brakes had created a speed regime where American pilots could aim accurately while Japanese gunners couldn't track effectively. But the technique's greatest impact wasn't measured in carriers sunk or hit rates achieved. It was measured in pilots who survived. The extended brake technique reduced G loads during pullout from 6.5 Gs to 4.7 Gs on average. That difference eliminated gin-induced loss of consciousness almost entirely. During the Philippine Sea operation, 0 SBD pilots reported blackout during pullout. 0 aircraft were lost to dive accidents. The technique that had started as unauthorized improvisation had become the reason American dive bomber pilots survived to fly multiple combat tours. By late 1944, as the war moved closer to Japan, the extended brake technique had evolved beyond its original purpose. Pilots were discovering that modulating brake deployment during the dive itself, not just during pullout, could correct for unexpected target maneuvers without breaking off the attack. If a ship turned sharply just before bomb release, a pilot could momentarily retract the brakes slightly, allowing the aircraft to accelerate and adjust aim, then redeploy them to stabilize before release. The technique required exceptional coordination and timing, but the best pilots made it look effortless. Lieutenant Commander Edward Heinemann, the engineer who designed the SBD's perforated dive brakes back in 1939, visited Enterprise in November 1944 to interview pilots about their experiences. When they described how they were using his brakes, Heinemann was stunned. He'd designed the system to eliminate tail buffeting and control dive speed. He'd never imagined pilots would use it as a variable drag control that could be adjusted continuously throughout the dive and pullout. When pilots explained how they modulated brake deployment to compensate for target movement, Heinemann asked them to demonstrate in the aircraft while it was parked on the hangar deck. He wanted to see exactly how quickly they could move the dive brake control lever and how precisely they could feel the brake position without looking at the indicator. What he discovered was that combat had transformed pilots into precision engineers of their own aircraft. They'd learned the exact feel of the hydraulic system, the specific pressure required to move the lever, the subtle feedback that told them brake position within degrees of deployment. They'd internalized the relationship between brake position, airspeed, and dive angle to the point where they could calculate intercept solutions in real time without conscious thought. Heinemann returned to Douglas Aircraft and briefed the engineering team on what he'd seen. His conclusion was that they'd accidentally created something far more sophisticated than anyone had intended. The perforated dive brakes weren't just drag devices. They were continuously variable flight controls that allowed pilots to precisely manage energy throughout the entire attack profile. The fact that pilots had discovered this capability on their own, without engineering guidance, proved how well the basic design worked. If the brakes had been difficult to use or unpredictable in their effects, pilots would have reverted to simple binary deployment. Instead, they'd learned to use them with surgical precision, because the hydraulic system and the perforated panel design responded smoothly and predictably to every input. The SBD Dauntless flew its last major combat mission on August 15, 1945, the day Japan surrendered. By that point, the aircraft had been largely supplanted by the Curtiss SB-2C Helldiver, a larger, faster, more heavily armed dive bomber that the Navy had hoped would be an improvement. But the Helldiver never achieved the SBD's accuracy or reliability. Pilots called it the big-tailed beast, and the name wasn't a compliment. The Helldiver's dive brakes were solid panels, not perforated. They created adequate drag but also created turbulence that made precise aiming difficult. The hydraulic system was faster than the SBDs, deploying in 2 seconds instead of 4, but that speed made modulation harder. Pilots couldn't feel the brake position as precisely. The Helldiver could carry more bombs and fly faster, but it couldn't put those bombs on target with the precision the SBD had achieved through its extended brake technique. Post-war analysis by the Naval War College calculated that SBD Dauntlesses using the extended brake technique sank or damaged 47 Japanese warships, including 6 carriers. No other American aircraft type came close to this record in the anti-shipping role. The total tonnage destroyed exceeded 300,000 tons. Individual pilot accuracy records from late war operations showed circular error probables as tight as 28 feet under combat conditions. That level of precision transformed the dive bomber from an area weapon that required multiple hits to achieve mission kills into a surgical instrument where 2 or 3 aircraft could disable or sink a major warship. The technique that had started with Lieutenant Commander Robert Dixon experimenting at Coral Sea, that had spread through informal pilot conversations at Henderson Field, that had been refined by dozens of pilots, whose names never appeared in history books, had rewritten the rules of naval aviation. The SBD's dive brakes hadn't won the Pacific War alone, but they'd given American pilots the tool they needed to sink carriers faster than Japan could build them. And the pilots had figured out how to use that tool in ways that no engineer or tactician or instructor had imagined. The final statistics from SBD operations tell a story of evolution through combat. From Coral Sea in May 1942 to Philippine Sea in June 1944, average dive bombing accuracy improved from 18% hit rate to 37%. Loss rates dropped from 8% per sortie to less than 2%. Pilot survival rates in aircraft that took battle damage and made it back to carriers increased from 43% to 78%. None of these improvements came from new aircraft or better bombs or upgraded engines. They came from pilots learning to use the dive brakes the way combat demanded, not the way manuals specified. The extended brake technique saved lives in ways that weren't captured in statistics. Every pilot who maintained consciousness during pullout instead of blacking out was a pilot who could react to threats, evade fighters, avoid collisions with wingmen. Every pilot who recovered at 1,300 feet instead of 800 feet was a pilot who had more energy to escape the target area, more altitude to survive engine damage, more time to make decisions under fire. The technique that seemed reckless to instructors, diving deeper before pulling out, holding brakes deployed when doctrine said retract them, was actually the safest way to dive bomb. It was safer because it kept pilots conscious and in control at the moment when they were most vulnerable. By late 1944, the youngest pilots arriving from training command had been taught the extended brake technique from their first day in SBDs. They had no memory of the old method, no experience with the by-the-book procedures that had killed so many pilots in early 1943. When they watched gun camera footage from Coral Sea or the early Guadalcanal operations, they couldn't understand why pilots were retracting their brakes so early, why they were pulling out so low, why they seemed to be fighting their aircraft instead of working with it. The transformation was complete. The unauthorized technique had become the only technique. The improvisation had become doctrine, and a generation of pilots who'd survived by violating orders had fundamentally changed what American naval aviation could accomplish. The legacy of the SBD's dive brake technique extended far beyond World War II. When Douglas Aircraft began designing the AD Skyraider in 1944, Ed Heinemann incorporated the lessons learned from combat pilots into every aspect of the new aircraft's dive brake system. The Skyraider's brakes deployed in 3.5 seconds, slightly faster than the SBD's but still slow enough to allow precise modulation. The panels were perforated with the same carefully engineered holes that had made the SBD's brakes so effective. The hydraulic system included detents that gave pilots tactile feedback about brake position without looking at indicators. Heinemann had learned that pilots needed to feel their aircraft, not just fly it by instruments. The Skyraider entered service too late for World War II, but flew with devastating effectiveness in Korea and Vietnam. Its dive bombing, accuracy, using techniques that traced directly back to the SBD pilots of 1942 and 1943, exceeded anything achieved in earlier conflicts. In Korea, Skyraider pilots routinely put bombs within 30 feet of frontline positions, providing close air support so precise that ground commanders called strikes within 100 yards of friendly troops. That level of accuracy wasn't possible with level bombing or glide bombing. It required the controlled descent that perforated dive brakes enabled, and the extended brake technique that pilots had discovered by improvising in combat. The last combat use of dive brakes occurred during the Vietnam War. By the early 1970s, guided weapons were replacing traditional dive bombing for precision strikes, but Skyraiders continued flying close air support missions until 1972. The pilots flying those missions, many of them too young to remember World War II, were using techniques that Robert Dixon had pioneered 30 years earlier. They extended their brakes early, held them through bomb release, retracted them during pullout. They modulated brake deployment to compensate for target movement. They understood that the brakes weren't just speed controls but precision instruments that let them put ordnance exactly where ground troops needed it. Modern naval aviation has abandoned dive bombing entirely. Guided missiles and precision-guided bombs deliver accuracy that makes traditional dive bombing obsolete. But the fundamental lesson that SBD pilots learned, that pilots in combat will discover techniques that engineers never anticipated, that effectiveness matters more than procedure, that the best doctrine emerges from the people actually doing the fighting, remains relevant. The F/A-18 Super Hornet pilots flying combat missions today are the intellectual descendants of Wade McClusky and Richard Best and Robert Dixon. They're still finding ways to use their aircraft that the designers didn't fully anticipate. They're still refining techniques through trial and error under fire. They're still learning that the manual is a starting point, not a conclusion. The SBD Dauntless itself survives in small numbers, preserved by museums and collectors who keep them flying. Approximately 40 SBDs remain in various conditions worldwide. A handful are maintained in airworthy condition, flying at air shows where they demonstrate the dive bombing technique that made them famous. Watching a restored SBD extend its perforated dive brakes and descend in that characteristic steep dive is witnessing history made tangible. The distinctive sound of air rushing through those 318 holes in each panel, the almost vertical descent angle that seems to defy physics, the controlled pullout that demonstrates how pilots learned to manage energy, all of it connects modern observers to a time when the outcome of the war hung on whether pilots could put bombs on carriers before those carriers launched the strikes that would sink American ships. The dive brakes themselves, those perforated panels that Ed Heinemann designed in 1939 to solve a tail buffeting problem, became the defining feature of the most accurate dive bomber ever built. Not because of the initial design, which was brilliant, but because combat pilots discovered capabilities that no engineer had imagined. The 4-second deployment time that seemed like a limitation became an advantage when pilots learned to use it. The massive drag that seemed excessive became perfect when pilots learned to modulate it. The simple hydraulic control that seemed adequate became a precision instrument when pilots learned to feel it. The transformation from design intent to combat reality, from what engineers thought they'd created to what pilots actually used, represents one of the clearest examples in military history of how warfare drives innovation in unexpected directions. Heinemann had designed a drag device. Combat pilots had discovered a variable flight control that could be adjusted continuously to manage energy throughout an attack. The designer had solved one problem. The users had discovered a solution to dozens of problems the designer never knew existed. That pattern, of users discovering capabilities beyond design intent, repeats throughout technological history. But in combat, where mistakes mean death and success means survival, the pace of discovery accelerates dramatically. SBD pilots didn't have years to experiment carefully in controlled conditions. They had seconds to figure out what worked while people shot at them. The fact that they succeeded, that they collectively developed a technique that doubled accuracy and dramatically improved survival, testifies to both human adaptability under pressure and the quality of the basic design they were working with. The dive brakes worked well enough, were intuitive enough, were reliable enough that pilots could experiment with them in combat and survive their experiments long enough to learn from them. The morning of June 4, 1942, when Wade McClusky led his dive bombers toward the Japanese carrier fleet, he was carrying with him the accumulated experience of dozens of pilots who'd learned through trial and error how to use their aircraft better than anyone had taught them. When his SBDs extended their dive brakes and descended toward Kaga and Akagi, when his pilots held those brakes deployed through bomb release and into pullout, when they recovered at altitude with speed and consciousness and the ability to evade fighters, they were demonstrating the culmination of months of unauthorized experimentation. The technique wasn't in the manual. It violated doctrine. It did exactly what instructors said would get you killed, and it won the Battle of Midway. 4 Japanese carriers sank that day. American dive bombers, using perforated brakes in ways nobody had authorized, had changed the course of the Pacific War. The brakes that should have been simple drag devices had become precision instruments in the hands of pilots who'd learned to trust their instincts over their training. The unauthorized technique had become the reason America won, and Ed Heinemann's simple solution to tail buffeting had become the most effective ship-killing system in naval history, not because of what he'd designed, but because combat pilots had discovered what else it could do. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.